Right. We are going to get to our inflection points. So something is a stationary point if the derivative is 0. Something is an inflection point if it changes from concave up to concave down. So a stationary point of inflection is a point where the tangent is still has a slope of 0. The tangent line has a slope of 0. The graph changes either from concave up to concave down or concave down to concave up, where the curvature is like the smiley or the sad face. But the gradient or the slopes of the tangent line, so notice here, my slope of my tangent line would be positive. Here, my slope of my tangent line stays positive. So if on your sine diagram you have a stationary point, but the sign does not change, then you have a stationary point of inflection. If you have a stationary point of inflection, inflection points always have a second derivative equal to 0. Inflection points have a second derivative equal to 0 and change from sad to happy, concave down to concave up. And so we'll be doing math with inflection points as well. So here we go. We have x cubed plus 3x squared plus 1. We want to find the coordinates of all the stationary points on the curve. Determine their nature. Are they maxes? Are they mins? Are they stationary points of inflection? And sketch the graph. So how do we find stationary points? We use our derivative and set our derivative to 0. You can factor out a 3x and you get 2 stationary points. Are there any non-permissible values? No. So the only critical points are your stationary points. You put them on your number line and make a sign diagram to figure out where things are positive and negative. And again, I labeled that line with f prime of x to remind me when I'm trying to find out where things are positive, I'm plugging numbers into my derivative. And I'm trying to find out where things are negative, I'm plugging things into my derivative. For me personally, I find it's actually the easiest to do your sign diagram if you use your factored form. So I'm going to put a green box around this factored form. And you start from left to right. So for example, and I'm going to do this in orange. This is so exciting. Last couple of days my orange pen wasn't showing up, so I'm very excited to see it again. If I choose something less than -2, like -5, can you see that this first factor is not orange? That first factor is negative. And if I plug -5 into this one would be negative. And a negative times a negative is positive. And the reason I like to go from left to right is because you start off negative. The next time I'm going to try something between -2 and 0, which is like -1. If I plug -1 into the first factor, it's still negative. I don't have to change that sign. But now when I plug -1 into here, this becomes positive. And like, ooh, I didn't have to erase anything. And now a negative times positive, this section's negative. And when I try something bigger than 0, like 7, no, I think I'll go 6. If I try 6, this will be positive. This is still positive. Positive on positive is positive. And then we can figure out these, because of this is going to be a local max, this is a local min, we can find the y values. And all of a sudden we're able to graph this. And quite accurate. You know that it's increasing, then decreasing, then increasing. You can label your maximums. often we like to also label x-intercepts. This x-intercept, I don't think we can factor that original equation nicely. So the only way you could find that x-intercept is with technology, either Desmos or your graphing calculator. And although you graphed x-cubed equations in grade 12 pre-calculus, you could only do them if they factored nice. And this one doesn't factor nice. And so this would be one you wouldn't have been able to graph nicely in grade 12. All you would know is, well, you would know the end behavior in grade 12, that is a positive x cubed graph, so it had to do that. But you couldn't actually find your x-intercept. You could find your y-intercept. But the best you could do is a table of values to get it. But now that we have the maximum and the minimum, drawing a smooth curve through those gets us quite an accurate graph. Second one. It's an x to the 4 graph. This one we could actually do quite a bit with grade 12, but we'll go over that in the end. So we need to find our stationary points. So we make the derivative equal to 0. Notice you can factor out a 4x squared. So we get x equals 0 and x equals negative 3. I put those numbers on my sign diagram. Again, I would use my orange pen. Yes, hopefully. And I'll double click it just to make sure. If I tried something less than 0, like a negative 1, can you see that this, as an x squared, is always going to be positive? So I can put a plus sign there no matter what. But when I plug in a negative 1 minus 3 is negative. This section is negative. When I plug in something between 0 and 3, this is still positive. But if I plug in 2, this is still negative. This section stays negative. But when I plug in something bigger than 3, like 4, now 4 minus 3 is positive. And my last section would be positive. And we have a graph with a stationary point of inflection because the sign didn't change. Still a stationary point, but now it has to be an inflection point because it's not a max or a min. 3 is still a minimum. We can plug in 0 and get 0, 0. We can plug in 3 and get 3 comma negative 27 as our key points. So to start off this graph, this is how I would start my graph. I would start with this point and this point. And then I need to decrease to here, decrease after to there, and increase. This would be a question where on this graph you could and would be expected to label this as well, 4 comma 0. Can you see on the original equation that you could factor out, I'll just write it here, if I made the original equation equal to 0, and I factored out an x cubed, I would get x minus 4. Can you see that your x-intercepts are 0 and 4? So from grade 12, pre-calculus, you would have known this, and you would have known the end behavior. And in grade 12, you would have said x equals 0 has a multiplicity of 3, so it had to flatten out or bend here. Now in calculus, we just call that an inflection point. And that inflection point naturally makes the bend because you have to change from here, concave up, to here, concave down. But calculus tells us how far down we would have to go. And grade 12 pre-calculus didn't. We just looped it back up. We knew there was a minimum, we just didn't know where it was. So now we are a little bit more accurate. Inflection points. So inflection points are where a graph changes concavity. They don't have to be stationary. You could have, for example, right? I'll draw an x cubed graph like this. This is the inflection point, because to the left of it, it is called concave down because it's sad. And to the right of it, it's called concave up because the curvature is happy. So something is called concave up if no matter where you draw your tangent line, your graph is above it. And we saw this with Mr. Bean with the linear approximation. If it's concave up, your linear approximation will always be an underestimate, remember? And if it was concave down, your linear approximation would always be an overestimate. P, Q, and R, it changes concavity. So these are inflection points. I'm going to color code this. Blue is concave up. Red is concave down. So concave up goes from -4 to 1, 3 to 6, and 6 to 8. 6 technically is nothing because it's a corner or a cusp. The endpoints aren't included because they're corners or cusp. We don't technically know what it is at that moment. And it would be concave down from 1 to 3 and 8 to 9. Now, are your notes were strategically designed in the next sentence to trick you later on in life, later on this year. So I'm gonna untrick you. Okay? This is gonna be what I'm gonna get you to do is to take out this word test and switch it with check. Small semantics, but it's going to be huge later on. Yesterday, we learned the first derivative test. The first derivative test finds maximums and minimums. Later on, we're going to learn the second derivative test. The second derivative test does not do concavity. So this would confuse you if you use the word test here. You think, oh, second derivative test, concavity. First derivative test, max and mins. We're going to learn later, the second derivative test is another test to find maximums and minimums. But you will always use the first derivative test. Okay, take that out, erase that. You will always use the first derivative to find maxes and mins. And you will always use the second derivative to find concavity. You will use the first derivative test to find max and mins. You will use the second derivative test to find max and mins, again, in a different way. Totally confusing because you will be trained to use the second derivative over and over again to find or check for concavity, but don't use the word test for concavity, because otherwise you're going to think the second derivative test is for concavity, and it is not. We're going to find out later there is a second derivative test, and it uses concavity to find maxes and mins. But you're going to confuse yourself with it later. And as much as I'm going to try to not get you confused now and again later, you will do it to yourself, guaranteed. But just warning you. So we use the second derivative to check for concavity. If your second derivative is positive is happy, it will be concave up. If something is concave, if your second derivative is positive, it tells you your first derivative is increasing. Notice that on something that is concave up, that as you go from left to right, your derivative is increasing. It's getting bigger. The lines are getting steeper. If your first derivative is increasing, your original function has to be concave up. And the second thing is if, I should do it even, right? Even in red. Notice your slopes are getting smaller. They are decreasing. If your slopes are getting smaller and it's decreasing, that means it's going to be concave down. So anytime your second derivative is less than 0, you know that your original function is decreasing, and you know that your your original function is concave down, and you know that your derivatives are decreasing. Don't want to confuse you later. Check for concavity. Yay. If your second derivative is positive, your original function is concave up. And if your second derivative is negative, then your original function is concave down. Somehow you have to remember negativity with sadness and positivity with happiness. However your brain can strategically do that will help you with concavity. If your second derivative changes sign from concave up to concave down, or vice versa, you will have a point of inflection. This is important. If someone says, hey, find a point of inflection, it is not enough to just show the second derivative is equal to 0. You have to show that it also changes concavity. I will give you an example. Here is y equals x to the 4th. What is the first derivative? 4x cubed. What is the second derivative? 12x squared. If you make your second derivative equal to 0, what's x? 0. If I make a sign diagram for my second derivative, we made sign diagrams for our first derivative, but we're going to have to make sign diagrams for our second derivative. And because I labeled it as second derivative, where am I plugging my numbers into? My second derivative. Something less than 0 negative 2. If I plug in negative 2 into here, do you see that this is going to be positive? If I plug in something bigger than 0, like 1, it's also positive. So even though the second derivative was equal to 0, this is not a point of inflection, because this means my original graph is concave up. Put F here, concave up. What does the graph of x to the 4 look like? It looks like a fat parabola. Does it have a change in concavity? No. It is always concave up. So we want to show that y equals x to the 4 minus 4x cubed. This is the one we graphed before, isn't it? We graphed this one just on page 15. Yeah, this is the exact same one we graphed on page 15. So you find your first derivative. But we're wondering about points of inflection, so I find my second derivative. If it's going to be an inflection point, we have to set our second derivative equal to 0 and solve. So possibilities of 0 and 2. And then, oh, I'm going to erase this. I like making. Oh, I've got the happy and the sad faces. They're not. I don't. Oh, wow. Oh. There we go. Oh. Really happy. Technically, I should have 0 on here as well. And what happens if you plug in something less than 0? Negative, negative. It's positive again here. Second derivative changes sign, and so the concavity changes. You need to show two things. You have to show that it changes sign and it's equal to 0. There is another way of showing an inflection point. This is almost never used, but I'll show it to you anyways. If the first derivative doesn't change sign and the second derivative is equal to 0, that's another way of showing that it would be an inflection point. This rarely comes up. I can see an AP thing trying to be sneaky in a multiple choice question to have something like this come up. But generally, the first way is intuitive. If it changes from concave down to concave up, that's what the definition of an inflection point is. That's the easiest. But the only way that that can happen is if your function also, the derivative, stays negative or stays positive at that point. So in grade 12, you would know the end behavior. You would have trouble with this one because you wouldn't know how to factor it. And it doesn't factor nicely. But now that we have calculus, we want to find and classify all stationary points and all points of inflection to be able to graph this. So I'm going to find my derivative. I'm going to factor it, set it equal to 0 so I can find my stationary points. Once I have my stationary points, I'm going to use a sign diagram to find out if they're maximums, minimums, or stationary points of inflection. There's my sign diagram. Again, I'm going to take out my fancy orange pen. There it is. And if I was testing something less than -1, like a -2, can you see this would be negative? And this would be negative if I use the factored form. And a positive number 3 times a negative is positive, telling me this section is positive. Okay? The arrows up and down, okay? The arrows are telling us stuff about F. The signs are in F prime. The arrows are telling us stuff in F. So it's increasing there. Then if I tried something between -1 and 3, I plug in 0. This is still negative, but this is now positive. So this section is negative. And if I try something bigger than 3, like 5, this will be positive. That stays positive. And so I find that using the factored portion, really easy for testing positive and negative. If you use the original one, oh, you've got to do so much mental math. Right? If I plugged in 5, I'm like, 3 times 5 squared. Oh, 75. Minus 6 times 5. Where am I at? Can you see the factored one? It makes it a little bit easier for you mental math-wise. So we now know that this is going to be a local max and this is a local min because the arrows are telling you stuff on F. The signs are telling you stuff on F prime. And I've actually seen some people do, oh, never mind. Exactly that. They label underneath with the F prime, and when they do the up and down, they label that with F. I'm going to show you something with the next one as well. Now I'm going to find my second derivative, which is really easy. Set it equal to 0, and I get x equals 1. Make my sign diagram. Take out my eraser. Okay. Concave down. I like the happy faces. Concave up. And I know that. Oh, it went. Why did it do that? My orange pen went away. Did you see that? That was very stressful for me because I really wanted to use my orange pen. So the plus and the minus, this is on F double prime. The concavity is on F. The negative can sometimes be seen as decreasing, right, and sometimes is increasing. That would be F prime. So your positives and negatives going up one level always does increasing, decreasing. So here, what's one level up from F prime is F. So one level up tells me F, increasing, decreasing, increasing. What's one level up from F prime? I mean F double prime? F prime. So F prime is decreasing, then increasing. What's 2 levels up from F double prime is F. 2 levels up will tell you concave up, concave down. Understanding these levels and how they move up and down is really important for some AP questions because they start you in the middle. They start you with the F prime graph and say, can you tell us something about the original graph or about the derivative graph? Or they start you with the second derivative. And can you tell me something about the f prime graph? And so knowing that your sign diagram, one level up goes increasing and decreasing, two levels up goes concavity. So now we can find these points. -1, 6 is our local max. 3, -26 is our local min. And 1, -10 is our inflection point. Personally, when graphing these, label all 3 points, but then when you actually go to graph it, start from your inflection point. Because this side is all sad, all concave down. This side in purple is all concave up. And if you start from your inflection point and draw concave down from one and concave up from the other one, it'll naturally draw nicely for you. So I actually find drawing a graph starting from my inflection point a really easy way to do it. So I'd like you to try the next one on your own. Oh, it has a calculator part. Okay, we'll do it together. If it was all non-calculator, I'd get you to try it on your own. Most of this we can do without a calculator. Process-wise, talk about when you're asked to sketch a graph with calculus. You're going to find your first derivative, draw its sign diagram, and that's going to tell you all of your local mins and local maxes. Then you're going to do your second diagram, second derivative, do its sign diagram. That's going to tell you all of your inflection points. Once you have all of your maxes and mins and all of your inflection points, you'll be able to graph it clearly. Other things that are nice to put on graphs, if you can, x-intercepts and y-intercepts. Sometimes you can do them without a calculator, sometimes you need a calculator. So, we want to sketch this graph using calculus. We start by finding our max and mins, our stationary points, by going to our derivative and setting it equal to 0. No calculator needed for this. When we solve, factor it completely because we have a difference of squares. We get 3 values. Now I'm going to take out my orange pen and I'm going to label f prime here and f there. So we plugged in values into f prime to find out it goes negative, positive, negative, positive. That tells us one level up that the original graph is decreasing, increasing, decreasing, increasing. And at this point, you might actually want to label those points. You can do this now, or you could do this at the end. How do we find the y-coordinates? You always find the y-coordinate of a point on your graph by plugging it into the original equation. So if I plug in -1, I get negative. If I plug in 0, I get 0. If I plug in 1, I get -1. Next, I take my second derivative. I set it equal to 0. And I get plus or minus 1 over the square root of 3. I think you might have been able to get away with this without a calculator. We do our sign diagram for our second derivative. Again, I'm going to take out my orange pen, and the positives and negatives come from f prime, concave up and concave down, and I am just going to make smiley faces because I like that. Positive, concave up, negative, concave down. And that is on F, up 2 levels for concavity. We plug those points in, and this is why it was calculator 0.6. Or negative 3/5 and positive negative 3/5 both times. Those are inflection points. They were not stationary points. They're just inflection points. I've labeled my inflection points in green. I labeled my stationary points in blue. And if I was graphing this, I would start from an inflection point. I would draw this all concave up. Then I would draw this section concave down. And then I would draw this section concave up again. Since it's a calculator question, could you label these x-intercepts? Absolutely. I've got one thing, this is 0, 0, sorry. There we go. Is that bothering you a little bit? Technically, you could solve these without a calculator. I'll label them. You could do your x-intercepts by setting your original equation equal to 0 and solving. Now, for the most part, up till now, we have been using calculus to do graphs that we mostly did in grade 12. Like you graphed x to the 4 graphs in grade 12, but you would have had to factor it completely and then use n behavior, and you would have never been able to label exactly where the minimums were. You just had x-intercepts and n behavior. Now adding those minimums and maximums and the inflection point, it draws a very accurate graph. Okay? But we can also use calculus to graph things that we did not even attempt to do in grade 12. Take a look at that next equation. Graph negative e to the x times cos. Definitely would not graph that in grade 12. And we're only going to graph it on the interval from 0 to 5 pi over 2. Whew. How do you find x-intercepts? Put y as 0. And we have to do a little bit of analysis here. Okay? You need to recognize in questions where you have an e to the x or e to the minus x, you have to know what the e to the x and the e to the minus x. I've drawn little tiny graphs up here. Maybe I'll label them. These are exponential graphs. This one would just be a flip over the y-axis, e to the minus x. Do you remember your e to the x graphs? Had an asymptote here. Wow. There we go. At 0. They had no x-intercepts. In other words, e to the x is never equal to 0. So the only place this could be equal to 0 is if cos of x is equal to 0. And that happens at pi over 2, 3 pi over 2, also 5 pi over 2. And it would keep happening, but we are only looking between 0 and 5 pi over 2. So those would be my x-intercepts. Technically, y-intercept is very easy to find. Let's just do it for fun. I'll probably do it later on, but how do you find a y-intercept? Plug in 0 for x. Let's do some mental math. If you plug in 0 for x, what is e to the 0? 1. What's cos of 0? 1. I know, I'm pushing you. It's first week back. What's 1 times 1? I know. Okay, I'll do it for you. Yes, so we get 0, 1 as our y-intercept. Next, find the coordinates of the first 2 stationary points and sketch this graph. So how do we find stationary points? We use our derivative. What would we have to do for the derivative here? Use our product rule. Keep one the same, derivative of the second one. Keep the second one the same, derivative of the first one. And do you see with the derivative of the first one, you have a chain rule. It'd be e to the negative x, but then you still have to multiply by the negative 1. We set this equal to 0 and solve. And in solving, you're going to need to factor out the common factor of e to the negative x. In fact, I factored out an extra negative as well. Why is that important? Just like this was never 0 there, can you see that here it would never be 0 either? So we just need to see where the inside part, sine x plus cos x, is equal to 0. In other words, where is sine x equal to negative cos x? Maybe you can do that from your pi plate, recognizing the root 2 over 2 ones, where 1 is positive, 1 is negative. Or, sorry, it's getting slow. If you divide both sides by cos, you see that that would change it to tan? And then it might be easier to see your pi over 4 family answers. When is tan x negative 1? Definitely pi over 4. Quadrant 2 and quadrant 4. And again, it would happen over and over again, but it only asked us to find the first 2 stationary points. So we just had to do 3 pi over 4 and 7 pi over 4. And then we could do our sign diagram. Our sign diagram says that it's positive here, negative here, negative there. You'd have to plug in values into your equation to check that. Try to use values from your unit circle that you know. So I would probably choose in between 0 and 3 pi over 4. I would pick pi over 2. Between 3 pi over 4 and 7 pi over 4, I would probably pick pi. Because those are easy values for sine and cos to figure out. And here I would pick 2 pi. So on our derivative, we had the sine diagram. That means our original equation is going up and down. This question was also labeled as a calculator because plugging in these values to get those answers would not be easy without a calculator. Does anybody know e to the negative 3 pi over 4 in their head? I know a couple of these. So as a result, wow, scroll up a little bit here. Oh, I don't even have it. We've got our minimum, we've got our maximum, we've got our x-intercepts technically. It's not to scale, but this would go up to 1. Because we found out our y-intercept was at 1. The question didn't ask us to find our inflection points, so we didn't bother doing that. But if you wanted to have a more accurate graph, you would have found out that there is an inflection point probably about here. And there might have been another one here. But we can now graph complicated things accurately if we wanted to. Yeah, I know you're thinking, why would I want to? All right, this is where we'll stop for today. You can have the last 10 minutes to work on your take-home quiz.